Hello everyone, welcome to our differential equation class. In this video we are going to talk about modeling applications. We are going to start with a review of what we know about the solutions of the logistic equation. Then we are going to introduce a new equation that is called the logistic equation with a constant term. And we are going to use all that in an real-life application or close to a real-life application. In our case, we are going to talk about hunting a population of deer, and we are going to try to answer one real-life questions that could be of interest for the people hunting the deer. So that's our plan for today. Let's start with a brief review on the logistic equation. The logistic equation is an equation that describes the evolution in time of populations having finite food resources. So the main variable in the equation is called the p of t, the population at the time t. Then the equation is given by p prime, the derivative of p with respect to time, proportional to a constant r times p, here we have it, then minus a term that is proportional to p squared, and divided by some constant and multiplied by the constant r. So the constant r is positive and is called the growth rate and has units of 1 over time, while the constant k is also positive, is called the carrying capacity and has units of individuals. So, and we know, one thing we know about this constant k is that the k represents the maximum population sustained by the resources available. And this equation has equilibrium solutions, and equilibrium solutions are constants that satisfies the equation. So a constant p is an equilibrium solution if and only if, when we put it into the equation, is solution of the equation. Because it's constant, the derivative is going to be 0, and then we have all these two terms equal 0, and that means that either p is 0 or this factor is 0, and if this factor is 0, then p is k. So we have either p equals 0 or p equal k. So this is what we know from before. The equilibrium solution 1 is 0, or the other equilibrium solution, let's say equilibrium solution 2, is k. And we did a study of a qualitative study of the solutions of the logistic equation, and we ended up with a graph something like this. In this axis, vertical axis, we have p. In the horizontal axis, we have time. And then we discovered, by studying the right hand side of the equation, that if we have initial data on this region, then the solution with that initial data has to be decreasing in time. If we have initial data in that region, the solution has to be increasing in time. And if we have initial data in that region, the solution has to be again decreasing in time. And we know that k and 0 are equilibrium solutions. That means they don't change in time. And all that information, together with the fact that solutions cannot cross, there are no crossing of solutions of differential equation, all that information give us these pictures for different solutions of the differential equation. So the solution have to behave in this way, where here we have a constant solution and here we have another constant solution. So we see that solutions with initial data in this region, when time increases, they try to get closer to the constant solution k, to this solution. Well, we call that solution an equilibrium solution that is stable, a stable equilibrium solution, because of that property. All the other solutions, even they have very different initial data, they try to get close to this solution. The opposite happens to the solution p equals 0. The solutions try to get away from that solution even though you have initial data very close. It doesn't matter, the solutions try to go away from that solution. So we call that an unstable equilibrium solution. Recall what we mentioned before, that the solutions do not cross or they cannot touch. And one last comment about this picture is that we are interested in populations. Populations are described by the values of p that they are 0 or positive, so p is in that region. As function of time, we are interested in this region, not here, and we are not interested in what happens in negative times around here. We are not interested. We put the origin of time where we are interested, and we study the solutions in that region. That's what we say here. So solutions are defined the populations. We study populations for t positive and for values of p positive. So let's say that positive. But actually, solutions are defined for all values of the t variable. We are interested in looking at this region, but they are defined everywhere. And if we see how the solutions behave everywhere, we are going to see that the solutions have essentially this S shape. So we have two constant solutions, 0 and k, and then the solutions are symmetrical around t equals 0. This is the part of the solution we are interested in populations, but the mathematical solutions are defined for all real numbers. And these are the typical S-shaped solutions associated with the logistic equation that you can find in the literature. Let's move on to the equation that we want to study in this video. That would be the logistic equation with a constant term. The equation looks like this. P prime is equal the term that defines the logistic equation plus a term that we call it m for migration, and this m is a constant, so that constant has units of individuals over time, because this is what the units on the left hand sides are. Therefore is a rate. The migration rate is called that constant, and that constant can be either positive. In that case we are going to call it I for immigration. That means that individuals are entering into the population. Or the constant m can be negative. In that case we write it as negative E for emigration. Individuals are leaving the population. And the name can also change. The name of the constant, we can call it, instead of negative E, negative H, where again H is positive and stands for hunting or harvesting. So the name of the constant may change with the application we are interested to study. More remarks. This constant m, what it does is shift vertically the parabola that is defined for m equals 0. When m is 0, this function here is a parabola. So the case m equals 0 is the logistic equation. Recall, this is the logistic equation when we have this right hand side, and this function here is actually a parabola when we graph that function as function of p. So this is a parabola. The parabola opens downwards because this term gives you the p square, which has a coefficient negative 1 over k, so opens downwards. Where are the zeros? Where the zeros are easy to obtain and they have a physical meaning. These are equilibrium solutions of the differential equation. When you go here and you look for solutions, suppose suppose this term is not here, and you look for solutions that they are constant, that means p prime equals 0, so this is 0, so that constant has to be solution of the right hand side equals 0. These are the equilibrium solutions. So solutions of this equation, but they are super simple to find because what we have is r p 1 minus p over k equals 0. We can cancel the constant r because it's different from 0, and then we have either this is 0 or this is 0. Okay, so this implies that one solution, for example, solution plus, is going to be k, and the other solution, the solution minus, is going to be 0. And these are our equilibrium solutions. Okay, what happens when we have a non-zero migration term? Well, we could have an immigration case, which we have it here. Immigration, that would be the case when the migration term is positive, and then the function that we need to graph is this parabola plus some positive constant. So what is happening is we are shifting the original parabola for the logistic equation. We are shifting this parabola up by some quantity, the immigration rate. Look what happens with the equilibrium solutions. These were the old equilibrium solution for the logistic equation. When we move the parabola up, the roots, they move to the right and to the left. So we are going to have one root that is negative, the other is positive. These are the interval of increasing, decreasing solutions that from the graphical analysis we are going to do in a minute. What happens when we have a emigration term? Well, then the constant m is negative e, and the function we have to graph is this function with minus this constant e here. So what is going to happen? The original parabola now is going to be shifted down, which is what we have here. And now what happens? This is the original parabola. The original zeros, k and 0, now they move inwards. The 1 0 move to the right, the other move to the left. And actually we have formulas for these zeros. It's going to be important when we study the solutions of the logistic equation with the constant term to find this equilibrium solution. P plus and P minus are equilibrium solutions of these equations. So the equilibrium solutions of the logistic equation with the migration term, here in this equation this constant is positive, this constant here is positive, recall carrying capacity, growth rate, and m can be positive or negative. Well, the formula for the solutions for the roots, it changes a little bit in the case m positive or m negative. In the case m positive, they are given by this formula where we have k is the carrying capacity, appears twice, and then alpha square is a number that is given by this expression here. It has the carrying capacity, the rate, and the immigration constant. And then when these are the two roots here. In this case, we have a slightly different formula. The 1/2 k is the same, the plus minus is the same, but now here instead of plus alpha square we have minus alpha square, where alpha square now has the emigration constant. The other alpha had the immigration constant. It looks like they are the same, but actually alpha is not, so let me emphasize this, alpha square is not 4k m over r. Instead is 4k absolute value m over r. So let me write it here. Alpha, actually, we can have one formula in both cases, and is 4k over r absolute value of m. So this formula gives you that when m is positive, and it gives you that when m is negative. How do we obtain these formulas? Well, this is left as an exercise, but the only thing you have to do is find zeros of parabolas. So what parabola? This parabola here. So put this equals 0, that equals 0, and use the usual formula for the zeros of a parabola, which is given by this formula. This formula gives you these two cases. Notice that in this case, the immigration case, what we have inside the square root is always positive. K is positive and alpha is positive, and we are adding them up, which means we always have one solution that is positive and the other solution is negative, because this number is bigger, the square root of that is bigger than k. So when we add up, we get bigger than 2k, and when we subtract, we get something that is negative, which is what we see in the picture. Good. In this case, we have k squared minus alpha squared. And here the first thing we have is that whatever is in the square root is smaller than k. Smaller than k. Because we are taking something positive of k squared and then computing the square root. Which means that the root plus is positive, but the root minus, because this number is smaller than k and here we have k, is also positive. And this is what we see here. The two roots are positive. One moves to that side, the other moves to that side, but both are positive. P minus is positive. Now, when this alpha that depends on the immigration constant is too big, this is going to be 0. And we are going to have one root, which is the case when the parabola is here. And if we keep making this constant more negative, then the parabola is going to be down here. And then we are not going to have roots. So let's study all these three cases in detail, especially the corresponding solutions to the differential equation in these three cases. This case, and this case. Let's see how the solution of the differential equation looks like in these three cases. So let's write down the three cases in a little bit more detail. Let's focus on the emigration case only, and we have three cases. Recall, these are the equilibrium solution for the emigration case, and the three cases are this, and that. You see, when the constant inside the square root is positive, when it's 0, and when it's negative. What happens when the constant is positive? Well, we have two roots, the p plus and the p minus, which one is bigger than the other, and both are positive. So we are in this case here. And that happens when k squared is bigger than alpha squared. What is alpha squared? Is given by this formula. So let's write it down. It's bigger than 4k e over r. Okay, so now we can cancel that k with one of these k's. We can then multiply everything by r, which here is going to cancel. We can divide by 4, and that is our emigration constant. This is a condition on the emigration constant, and the condition is that the emigration constant has to be smaller than rk over 4, and we are considering the case emigration constant positive. So when the emigration constant is positive but not so big, smaller than that quantity, then we have two different roots. But when they are equal, in this case, then we are going to have, what is going to happen in that case? In that case, this constant is 0, so that disappears, and then the plus minus disappears, and both roots are k over 2. So in this case, we have p plus equal p minus equal k over 2, which is what happens when we move this parabola all the way up to here. That here is exactly k over 2. That's k. Okay, and for that particular, that fixes a value of the the emigration constant because k squared is equal alpha squared. Recall alpha squared is 4k emigration constant over r. So we do the same cancellation as before, and we end up with now emigration constant equal rk over 4. This is for that emigration constant. We have only one root. And now what happens here? Well, when this is negative, the roots are complex valued, which means they are not real valued, and we are in this case. There are no roots. So we have here no roots, no real roots. The roots are complex, but they don't have any meaning for us. So we are not interested in them. And when that happens when k squared is smaller than alpha squared, that is 4k emigration over r. Of course, we do the same cancellation, and then we end up with, when the emigration constant is too big, bigger than r k over 4, then we don't have any equilibrium solutions in the differential equation. Let's see the implication of these three cases, and also including the logistic equation in the solutions. So what we are going to do is we're going to focus again on this right-hand side of the equation. Now we change the constant on purpose to something else, so hunting in this case, but you see it's negative, so that's all it matters. Negative or 0. And the case 0, recall, is the logistic equation. We have seen that in the previous video. This is the case h equals 0, logistic equation. We have our parabola, the roots, one root is 0, the other root is k. These are equilibrium solutions. What we do here, this is the interval of the solutions of the differential equation, of the logistic equation. This is the interval where the solutions are decreasing. Here they are increasing, here they are decreasing for initial data over there. What that means, recall from the previous video, we grab this axis, we put it as a vertical axis. Now we introduce time. We copy the equilibrium solutions. These are equilibrium solutions at k, that means equilibrium solutions as function of time. Then these arrows here mean that the solutions have to be decreasing. Solutions do not cross, so it had to be something like this. Here the solutions are increasing. The solution has to be like that. And down here the solutions are decreasing. And this is the graph of the solutions we obtained in a previous video as function of time, a qualitative graph, which is right here. And now the only thing we have different is we are calling the equilibrium solution P plus and P minus. Cool. Now let's go to the case where h is the hunting constant, or harvesting is, or emigration constant is not so big. Then we have two, like we mentioned before, we are going to have two real roots. The root corresponding to the logistic equation, that it was k in the logistic equation, moves to the left. The equilibrium solution 0 in the logistic equation moves to the right into P minus, P plus. And if we do the analysis that we did before here, but with this picture, we obtain this picture here, where we see now that the constant k is no longer an equilibrium solution in the case of hunting, because the equilibrium solution is P plus, so which is smaller, and P minus, which is larger than 0. These are the equilibrium solutions. The behavior is the solutions are decreasing when for this initial data below P minus. So here, any solution here decreases in time. Solutions between the two roots are increasing. They cannot cross, and the solution above P plus, they are decreasing. So the picture is very similar to the previous picture, just instead of at 0 and k, now at P plus and P minus. But because of the P minus is positive, we have something interesting. There is a region here that if you have initial data in that region, look what happens. The solution have to be decreasing, and at some point they cross the horizontal axis, which means the solution becomes 0 at a finite time. 0 at a finite time. What does it mean population 0? Well, the population went extinct. It disappeared. So now we have a region of initial data where the evolution of that initial data gives you the evolution gives you a population as function of time that goes extinct in a finite time. So this region here of initial data where the solution is gonna go to 0 in a finite time, we didn't have that before. Before we didn't have that at all. Now with hunting, we have that region. This is called extinction zone, and the extinction zone is the zone of initial data where that happens. This is a new behavior when we add hunting to our system. Now what happens when the hunting is higher? Well, when we reach this specific value of hunting, recall we get only one root. So this is the picture now. We have shifted the parabola so much down that we have the two roots coincide in one value, which has to be k/2. So what happens with the solutions now? Well, the solutions of when we add time, they look like this. The two roots that we had here have approached some middle point, and that middle point is k/2, exactly between k and 0. And now we have only one solution. The solutions are decreasing for higher values of initial data than k/2, so the solutions are decreasing. They cannot cross the constant solution. And here they are also decreasing, so the solutions also decrease. So we see now that all these solutions go to 0 in a finite time. So all these solutions here go extinct in a finite time. Okay, so let me change the color into the color I was using, which is this color. So now that is much better. And now let's put here that these are solutions that they are going to 0 in a finite time. So the extinction zone now is larger than before. It grows with the root p minus. So now this here is the extinction zone. It's larger than before because it grew when we increased the coefficient h, the harvesting or hunting coefficient. What happens if we increase it even more? Well, you know what is going to happen. When we increase it more, then we are not going to have any roots because the parabola is too far down. So we are going to have only decreasing solutions and no equilibrium solutions. There are no equilibrium solutions at all. So this is what we get. No equilibrium solution. I'm marking here where k is and where 0 is and where k/2, but these are not equilibrium solutions anymore. These are solutions, you see, that behave like the other solutions. So because of the hunting term, that is too large. So now every single solution, no matter where it starts, goes to 0 in a finite time. So let's add this here just to emphasize that. And this one here to emphasize that. And this one even here to emphasize that. So we have solutions that all the solutions go to 0 in a finite time. And therefore, the extinction zone now is any point on the positive vertical axis. So now all that is the extinction zone. And this is the behavior of the solutions of the differential equation called the logistic equation with a migration term. Depending on the migration term, especially in the emigration case, we can have solutions that behave like this, or solutions behaving like that, or solutions behaving like that. The important new behavior is that we have this extinction zone that we didn't have before, and when hunting is too big, the extinction zone goes for every value of the initial population. We are now finally ready to go to the main part of our class, which is the modeling application we are interested in. And here is the situation. We want close to a real-life situation that we can solve with our mathematical models. Suppose that we have a deer population, and the deer population is living in a close valley, somewhere in between the mountains, in a close valley, and because of that, the deer population has finite food resources, and there are no predators. They can live there freely, but the amount of food is finite. Okay, suppose that the deer growth rate, so how they reproduce, is r equal to 1 over year, which means that usually they have an offspring of two little deers per year. Okay, and also suppose that the valley can sustain up to 10,000 deer. And suppose that right now, if you go and look and count, you have 3,000 deer. Okay, this is the situation. Now, suppose they are hunters on that living on that in a village on the same valley, and those hunters, they have a very interesting question. They want to know what is the maximum number of deer they can hunt so that the deer population does not go extinct, because they want to live there for a long time and they want to hunt deer, but they don't want to overhunt, because then the population of deer go extinct. How much it is? What is the maximum number of deer they can hunt? Is 1,000? Is 100? They want to know. Okay, so then we can use, this is a good situation where we can use all we know about population with finite food resources and a constant term. So what we need to do first is to set up our model that is appropriated for this situation. First of all, we are going to have our function p of t that is going to be the deer population. Deer population this is the deer population at the time t. At the time t. That is the easy part. Okay. Now we know that the deer population have finite resources. Deer. This is not that deer. It's this deer. The deer population have finite resources. Okay, so we know that there is an equation that describes that situation, one of the simplest equations, and that equation is p prime of t is equal the growth rate and then 1 minus p of t over k. This is what happens to the deer population, what should happen to the deer population if there are no predators and there are no hunting. And what are these coefficients? Well, these coefficients we need to measure from our system. In this case, they have been measured for us, and we have that R is 2 and the K, the carrying capacity, is 10,000. So we know that R is 2 1 over year. So here we are choosing what is our time units, years. If you choose the units to be months, okay, then this coefficient has to be divided by 12, because this coefficient is 2 years per year. If you are choosing days, well, you need to divide that by 365. So choose the unit of time, and based on that, this is how you compute what is the growth coefficient. And k, well, k is independent of time. K is a number of individuals, is the number of individuals that can be sustained by the food resources available. So these are individual. Okay, that is what would happen if we don't have hunting. But now, to our model, we need to add hunting, because this is what happens to the deer if they are alone. Okay, we add hunting to the model. Okay, so what is going to be now the model? The model is going to be the same as before. P prime of t is equal, actually let's put the data that we have. The data we have is 2 p of t, then 1 minus p of t divided by 10,000 minus some coefficient h. And this is what we want to find now. Our main unknown is h. We all we know is that there are hunters, so h is positive. And the other thing we know is that the initial population is, let's call it p at 0, and p at 0 is 3,000 individuals. Okay, that is what we know, and recall we are trying to find h so that the population does not go extinct. So what is then the problem? The problem is we need to find the largest value of the constant h so that the deer do not go extinct. So now we need to use what we know about the solutions of equations of this type with a constant h here. And this is what we know. We know that we have, in this case, a deer population, a carrying capacity of 10. This is going to be the equilibrium solution if we don't have hunting. Recall? And 0 is the equilibrium solution if we don't have hunting. But we do have hunting, but we don't have too much hunting. So we are going to add a little hunting so that this root is going to go down a little bit, this root is going to go up a little bit, and we are going to end up, and here we have a, say, this is k over 2, which in our case is 5,000. Recall, k over 2 is an important number, because this is where the two roots are going to go if the hunting is too much. Let's put it here. Okay, so where is our initial data? Our initial data actually is more or less around here. Here is P0, P at 0, and let's call it also P0. And that is going to be what we have right now, and it's below k over 2. So now we need to increase the hunting coefficient so that what is going to happen when we increase the hunting coefficient? Well, this root is going down, this root is going up, and we don't want the root p minus to go over the initial population, because if the roots p minus is here, this initial population is going to go extinct, and we don't want that. So we want to increase the hunting coefficient so that here we have p minus, and more or less over here we have p plus. This is going to be the constant solution p plus, this is going to be the constant solution p minus, and we want to increase the hunting coefficient so that these roots do not go over the initial population. So in that way, the extinction zone our initial data does not go into the extinction zone. So this is gonna be the extinction zone. And the extinction zone, we wanted to recall this is p less than p minus, bigger than 0, and we really want that our p0 be outside the extinction zone. That is what we want. So our initial condition, this initial condition right here, has to be outside the extinction zone. That's the condition we are looking for. So with that, the hunting must be smaller than the critical hunting. And what is some critical hunting, not the same as before. We need to find what is the critical hunting. The critical hunting here, HC, this is not K over 2, this is smaller than that. The critical hunting is such that P0, the initial condition, is the root P minus. You see, when the hunting that the hunters have to do has to be such that this root is smaller than P minus is smaller than P0. So let's compute the critical hunting when they are equal, and then the hunting done by the hunters has to be smaller than this number HC. Okay, and recall P0 is 3000. Alright, but we are going to call it P0. We are not going to replace it 3000 because it's too big. Okay, so let's put P0 has to be equal the root P minus. But we have a formula for P minus, isn't it? The formula is all the way up here. Here is the P minus is with a minus here. This is the formula where recall that was now with an H. This is what alpha square is. That is P minus. So let's go all the way down. And now in our problem, P0 has to be equal to 1/2 K. I'm going to call it K. We know what K is, but I don't want to write 10,000 all the time. Square root of K squared minus alpha square. That is the root. And recall alpha square is 4K H. This is the H critical over R. Okay. So that is what we need to solve. So what we're going to do is we're going to multiply by 2. Now it's algebra. It's just algebra. We need to recall HC is what we have it in here. So HC is there, and we want a formula HC equal something. So we need to compute that in terms of the rest. So the first thing we are going to do is multiply by 2. P0 is equal K minus square root of K squared minus alpha squared. We are trying to isolate alpha first. Okay, so what do we do now? Well, we move the K to the other side, or better, let's move this term to the other side and this here. Let's do that, and then we are going to have here square root of K minus alpha squared, K squared minus alpha squared. That is horrible. So let's try again. K squared minus alpha squared, square root. And on the other side, we are going to have K minus 2P0. Okay, and let's try to make the equal sign equal. We are not going to be, it's not possible, but we can. Yes, it's possible. Really likes the equal sign one after and below the other. Okay, so what do we do now? We compute the square on both sides. So we compute the square, and then here we are going to have K squared minus alpha squared, and over here we are going to have k minus 2p0 all squared. But we know what that is. Recall that we have a little formula, let's put it in green, that whenever you have a plus b squared, this is a squared plus the double product ab plus b squared. So that formula here with a if you have a minus sign, of course, is a minus there. So then we are going to have here k squared minus the double product, so we are going to have a 4 p0k, and then plus 4, which because it's 2 p0 squared. Okay, so the first thing we can do is that k and that k, they go away. Okay, and what else we can do? Now is a good time to replace what alpha square is. Alpha is that. So we are going to replace, and then we are going to have minus alpha squared, which is 4k, the critical hunting over r. And here what we have is minus 4 p0k plus 4 p0 squared. Okay, that is just fine. So we have 4, 4, 4 in all terms, so we can cancel the 4s. We can cancel this 4 with this 4 and this 4. Good. What else we can do? We can multiply everything by r. We can multiply everything by r. So we can multiply here by r, and we can multiply here by r. This r is going to cancel that r. And then we can multiply everything by -1. And we are going to end up with k, hc. And over here we are going to have positive r k p0 negative r p0 square, negative p0 square. That is what we are going to have. What else we can do here? So we can divide everything by k now. So now what we are going to do is we are going to multiply by 1 over k, and we are going to multiply by 1 over k everything here. So these two are going to go away, and we are going to compute our critical hunting coefficient. Our critical hunting coefficient is going to be, recall that we need to distribute that. So what we are going to have, we are going to have r p0 minus r p0 squared over k. Alright, so maybe we can do one last thing. Let me put this a little bit higher up. The last thing we can do is we can pull common factor, and let me highlight it. We can pull common factor r and p0. Here we have r and one of the p0s, not two. So we end up with hc, that is going to be r p0 multiplied by 1 minus p0 over k. And this is the formula for our critical hunting. Recall, p0 is the initial population, and k is the carrying capacity, r is the growth rate, and this is our critical hunting. For our problem. This is for our problem. For our problem. Okay, so let's put the numbers. If you put 2 multiplied by 3000, and then 1 minus the 3000 divided the 10,000, and you do some calculations, you are going to get that this is equal 4,200. So individuals. Per year. Recall the units of the emigration term. So this is the critical hunting. You hunt that, and then your population is going to go extinct. Anything less than that is fine. So our hunting has to be less than 4,200 individuals per year. You want to be on the safe side, then we can say, for example, that a good hunting, the maximum possible, just to be sure, is 2,000. So with that, then you are far away from the critical hunting enough. So if we have some errors in the estimation of the coefficients, suppose we didn't compute the initial population very well, or suppose they have less growth rate than 2, or maybe there is less food than we thought there was in the valley. So with that margin, we are more or less safe. And that's how we solve a real-life problem for the hunters in the village using our mathematical models. Just one remark before we finish our video today. Suppose that P0 is P0 is the initial population. Let's take a look at this formula, because this formula for the critical hunting is kind of interesting. So let's take a closer look to that formula. What we found before is that we have R P0 1 minus P0 over K, isn't it? Which is actually the initial population, so population at time t equals 0, and then 1 minus population at time t equals 0 over K. But recall that when we have the logistic equation, P prime at t is given by that formula, P of t times 1 minus P at t over carrying capacity. This formula at t equals 0 implies what that implies. This formula implies at t equals 0 is that the derivative of the population at the initial time is R P at 0 1 minus P at 0 so over K. Okay, so we can rewrite our critical hunting coefficient as the population at 0 according the derivative of the population evaluated at 0 according to the logistic equation. Recall here we wrote the logistic equation. This is the logistic equation. So our hunting coefficient, the maximum, the critical hunting for our deer population can be interpreted as by this formula, where here P prime at 0 is computed without hunting, with the logistic equation, only with the logistic equation. So here is another interpretation for the coefficient we found in our problem. We should hunt no faster than the natural deer growth. This here is the natural deer growth. Natural because logistic equation. If you leave the deer alone, the natural deer growth with that initial population is given by this expression here. You should hunt less than that. On that note, we can finish this video, and let's hope see you in the next video.